Hello and welcome to this session on deep learning for recommender systems. First, a few words of introduction. My name is Oliver Gindele. I lead the machine learning team at Datatonic. And in case you don't know Datatonic, we're a team of data experts, data engineers, machine learning scientists that build bespoke solutions either on big data or machine learning for our customers. Work with customers across many industries. One is retail, and in this session I'm going to share some of our findings for when we work with these clients and build recommender systems and personalization engines. I'll start quite simple with introducing recommender systems and then show how this can be put into practice with TensorFlow. And then later in this session I'll also go into some of the more recent and more advanced methodologies and the novelties that come with bringing deep learning into the recommendation space. The good thing about giving a talk on recommender systems is I don't really have to introduce them. Most of you will probably be familiar with a user interface such as Netflix or Spotify's that recommends content to you directly. And the idea really is to match the right products or to match the right items to the customers, because if you think about Spotify, they might have hundreds of millions of songs. You don't want to go on there and just search through what new music you might be interested in. This is where recommendation systems come in. They will just find the content you want to interact with next. There's some less obvious use cases of recommender systems. And this might be Google Search, for example. So if I go onto Google Search and I type in Python, it looks like this. And this might look very familiar to most of you, but if you think about it and take a step back, I type in Python, but if I want to learn something about the snake, I have to scroll down and press page 2, and that's where I find that. So Google Search is heavily personalized, and it also highlights a bit how recommendations and searches or search indices are quite related, and I'll talk more about this in a bit. So how will we build such a recommendation system, Netflix style? Well, there's been a very famous approach called collaborative filtering, and it tries to squeeze out some similarities between users and similarities between items, and then kind of search that space and find what's close to each other. And one way to think about this is if you look at this pricing matrix here on the left. So imagine you run a web shop that sells books. You have N users, you have M books. And quite often, if you have many articles, this matrix will look quite empty. It will look quite sparse, meaning there's many of these empty fields because not every user will have the time to read every book, which makes it difficult to then find what other book might be interesting for a user. So the idea is, can we fill this matrix and guess the ratings and guess how likely a user is going to like a book they haven't read before? And then if we do that, we can just calculate approximate numbers and find the 5 highest numbers and serve them as the recommendations. So that's the whole principle. How we're going to do that in practice is we can use these collaborative filtering methodologies and factorize the matrix into a matrix U and a matrix V, which are on the right side here. By doing that, we do take another step. We actually condense and compress the space of this high-dimensional user space or high-dimensional item space into a low-rank format, which now has dimensional decay. By doing that, we kind of build a matrix that has some dense representation on users that's lower space, and the same goes for the items. And users that are quite similar should have a similar vector in these rows. We can now use this factorized matrix to find the elements we don't have yet. For example, this blue entity on the top left, we want to know, is this user very likely to be interested in a book, hence giving it a high rating? To compute this, we can just find the right row and multiply it with the right item column, and we reproduce this rating. So that's the idea. To put this into practice, we have to compute these numbers somehow. For that, we can use an approach you just write down the objective function, and then like with anything else in machine learning, we want to minimize this. And this looks quite simple. We have a ratings matrix over users and items, and we have this matrix X and a matrix Y, which are our lower space representations of the item and the user matrix. The error we're going to calculate is the distance. So we generate the new approximate rating, and we see how this compares to the actual rating. And that's what we minimize under the square. We can add some regularization, which are the terms in this lambda bracket, to just keep the weight space a bit smaller. So this approach of collaborative filtering became very popular almost a decade ago, and it's been widely used ever since. It's basically the de facto standard to recommender systems, or it's been over the past 5 years. It came out of what was called the Netflix prize, a $1 million prize to develop a very good recommender system on Netflix data. And you can solve this quite straightforwardly with established approaches. It's basically singular value decomposition, and you can use methodologies like alternating least squares or stochastic gradient descent to solve this objective function. These approaches are quite nice because they parallelize well. So if you think of Netflix, Spotify having a lot of data about their users and a lot of products, this is probably what you want to choose because you can scale out the computations. But if you just briefly look at this, it's quite clear this is a regression problem we want to solve. So now with this a bit abstract introduction to collaborative filtering, we actually want to put this in practice. One interesting use case might be finding love or finding interesting people and using the collaborative filtering framework. To get started, we obviously need some data. One data set I found is this Libemseti data set from a Czech online dating webpage. They released a rather sizable data set in 2005 of almost 20 million profile ratings, where a user rates another profile, usually of the other gender, and gives it a score between 1 and 10. The data set was released in 2005, but this screenshot is actually taken a few months ago. So this is how the web page looks right now, and it's still active and has some few hundred active users. So let's dive a bit into the data. It's a quite remarkable data set, given that it's over 10 years old, and we actually have more than 100,000 users. The majority of the ratings are actually female, and there's less a percentage of male. But if you want to have a look at the distribution of the rating, I think this is quite interesting. Because what we see is we have like a bulk part between kind of 6 and 8. We have many zeros, and we have even many 10s in ratings. And there's an interesting gender split there as well, which I think is quite remarkable, where if you look at the zeros, the gender split is quite equal, although we have many more female ratings. But the 10s, they're clearly female dominated. It's worth taking a note of how the data is actually structured here, and it's quite common for recommender systems. We have a profile ID, we have a user ID, and we have a rating between 1 and 10. What we also get here is the gender. But now armed with the profile ID, user ID, and the rating, we can basically build this matrix, and then we can try and fill it out and find the right matches for every user. So how are we going to do that? Well, we can use a computational tool like TensorFlow and put this into practice there. TensorFlow became very famous as a deep learning library, but I think this makes a great example to show that it's much more than just deep learning and computer vision and natural language processing. It's a very general framework to design computational graphs and execute them very quickly on things like GPUs or multiple processing nodes. So this objective function we've seen before, we can now go and put this into TensorFlow. And while we do that, I want to highlight a few of the newest developments that came out earlier this year that makes TensorFlow as accessible as ever. One is the dataset API, which allows you to quickly parse and build data, and also parse in data that's larger than it would fit in memory and parallelize it. So if you think, I can use pandas to do that, that might work for small sets of data, but if you have millions of users and gigabytes of training data, you might struggle with that. So the dataset API helps with this. There's also the estimator part, which is quite new, and it's basically a wrapper around the models that combines your model with the data, wraps it up in a neat function, and all you have to do then is write .train or .fit or .predict, and you don't have to construct the whole training loop yourself. Previously in TensorFlow, you would build your graph, a model function, and then you would create a session. You would loop within your session over the graph as many times, and you would calculate your gradients, apply the gradients, etc. You would write very verbose code just to train your model. Now it's very much Keras style, just .train or scikit-learn style, as you might be familiar with. The other nice thing as well is this estimator API allows TensorFlow to build these canned models. So there's already some models that are deep neural network regressors. There's some linear classifiers, and the community is heavily building around this framework as well and this API. So if you go into the TensorFlow API these days, you'll actually find things like booster trees already, Gaussian mixture models, k-means, clustering, or some time series models, autoregressive time series models. So there's a lot of pre-built functionality in there, and it's the encouraged way to build models and maybe also share them these days. The estimator will obviously connect to this dataset API via this input function over here, and I'll show you the details of that in a second. Another part of this high-level API picture is the feature columns of TensorFlow. These are interesting because they connect your data with the tensors in a TensorFlow model. And it allows you to do some neat things like one-hot encoding or bucketizing, building crossed feature columns, and just building representations of your data in tensors. So that's quite useful in the combination with the last two APIs I mentioned. Another interesting part I want to highlight here is this embedding column, because we're going to see a lot more of that in a bit. And the embedding basically calculates a dense representation of something like a one-hot encoded vector. But more about this in a minute. So now we got the data set. We got some idea of how to build a recommendation system by minimizing this loss function that I showed previously. So how does that look like in code? First of all, I'm going to go quickly through the dataset API, where we built this input function. And we start at the top, write a little function to parse and decode a CSV. Then we create a text line dataset somewhere in the middle here. And we can do a lot of things and a lot of pre-processing, and much of this can be parallelized and using with queues and efficient shuffle buffers, for example, to really optimize input pipeline speed. So there's shuffling, there might be caching and prefetching, some details we might not need to talk about. But at the end, you just create an iterator, which is basically a generator for TensorFlow to call and get the newest batch. Nice thing with the newest releases of TensorFlow is you can actually compress this into 1 or 2 lines. There's already a high-level function to just make a CSV data set. But if you need a bit more control, this is how you would do it. So we got the data in TensorFlow. That's fine. Let's build this estimator. With the estimator, we connect the model function and the input function into something that's very convenient to use. And for that, we need to define a little bit how we train. So we pass in an optimizer object. We tell TensorFlow how to optimize. We might also pass in some evaluation functions, etc. And then we just wrap it into an estimator object at the bottom of the code. And this is what we would run .train on or .predict, for example. So the last piece here is now the model. And this is where it gets interesting. So the model is actually kind of simple. We start with connecting, again, the data set to our tensor objects. So we build categorical columns from the user ID and the profile ID. We can also add some bias columns here at the top, because it might help to have bias in the object function as well. We transfer this into tensors in this step. We're going to split this just for convenience. And then the actual model, there's one step I'm missing, which is actually these embedding columns. And this is pretty much the core piece here. Because originally we parsed the user and profile ID. We one-hot encode them. as categorical variables. And now we use this embedding as a way to convert this into a dense format, and we can do this at this lower dimensional. So if you think back at this graph I showed previously, where we learned this sparse rating matrix and compress it into two matrices with lower rank representation, this is that step that does this for us. And we see we have a dimension, for example, 10, so we don't have 100,000 users anymore. We have something pushed into a 10-dimensional latent space. Further down, we can actually build our loss function. This is the core of it. This is actually this dot product that reproduces the rating. And then we can add the bias again, we can add some regularization, and in the end we take the mean squared error. So this is pretty much, that's all there is. If you think back of the objective function and the loss function I showed you on the previous slide, this is it in TensorFlow. So now we can go and actually train it on that data. But before we do that, we might as well take another step and leverage a bit what TensorFlow also offers, this whole functionality and ease of use for deep learning. Because what we've done here is we built a matrix factorization model represented in TensorFlow, but there's already a lot more we can do on a first glance. There's a paper on neural collaborative filtering, came out I think 2 years ago, which explores this matrix factorization already a bit more. So if you look on this left side here, we have a MF matrix factorization layer. It's exactly the code I just showed you. If you look down here, the inputs are these embedding vectors on either users or on items, and this is what goes into the layer. So far, so good. But how about we build another model over here, which is just a deep neural network. It's a MLP, a multi-layer perceptron, has a bunch of feed-forward layers. And we can train this on the same embeddings that we created for the matrix factorization. Or if you feel fancy, we can actually create another set of embeddings and let them train individually. But the idea is we built already a sort of ensemble model, because at the top we concatenate the output of these two models and then train our model on the loss that's joined on them. So part of this we've seen. The right side is quite trivial. It's just a few dense layers in TensorFlow. So you think, well, why are we doing this? It's obviously nice. We can call it deep or a neural recommender system, and we just make everything deep because it's better. Well, there's another reason. It's because we can easily add more data. If you think back of what we had on the matrix factorization over here, is we have a user ID, a profile ID, and a rating. Right? There's not much more, and people's been struggling for a decade to input more data in here. But with this MLP approach, it's a bit more straightforward. So what we can do is go beyond user ID and item ID, and we can embed context or metadata. This could be age, this could be a genre of a film, the length of a film, could be comments, etc., depending on the use case and the types of recommendations you want to do. But now this can be all inputted into the first layer of an MLP and then jointly trained with a matrix factorization model that's been in practice used for decades. So we're quite confident that the left side works. Now I'm going to show you how well this works in practice. So if you look at this table, we have the matrix factorization, we have the MLP, so these are separate, matrix factorization, separate MLP, and then we have this joint model I just showed you on the last slide. The error we're going to look at for now is root mean squared error and mean absolute error. And we see we want to minimize this, the error should be as small as possible. Comparing MLP is already slightly better than the matrix factorization on its own, but putting both together into one model and jointly training them seems to yield the best results. And this is even just on that data set I showed you. I also compared this to some research data I found. There was one paper that's built a similar system almost a decade ago. They used some SVD approach, some more standard matrix factorization approach. And the results are actually quite comparable. So just fiddling with this for a few hours, we get you could call it state-of-the-art performance. But I'm also not entirely sure whether the data set these researchers seen is the same as what I've seen. In any case, what we see is putting these two parts of a model together into an ensemble already yields very good results. And TensorFlow is a great tool to do so because it allows us to quickly put something into practice that might be coded up in other Python libraries like SVD, but we can build it from scratch very easily. And it also allows us to extend it as we like by changing the loss function, by using some other layers and combining them. So this was already quite nice, but there might be some ways where we can do better. First of all, it's always about the data, and I think we strongly believe when we work with clients on such problems that more better data, whatever this means, will yield a lot better results. So now that we've seen that we found a good pathway to put in more data about users or films or anything in terms of context or metadata into the model, and it also seems to improve the results, we should maybe focus on collecting more of that or tapping into more of that. There's things like personal details, there is demographics, there is online behavior. If you think about a retailer or an e-commerce platform, there's browsing journeys. There might be third-party data you can buy in and learn more about your users or more about your products as well. Maybe there's information to be gained from parsing some of your films and looking at its content in terms of speech or in terms of video. So building these top rows here, as in building a very good single customer view that gives in-depth details on who your users are and who the products are, it's probably quite beneficial. And if you're new to machine learning or recommender systems, this is probably what you should focus on. And what I'm going to tell you in the next 50 minutes, you can safely ignore. We definitely believe that there's a lot gained to improve your data first. That will always outweigh improvements in modeling, etc. There's another really important aspect here, and this is when you look at these blue tabs. This data cannot just be used for recommendations. It goes way beyond. There's a whole lot you can do for personalization built on a good single customer view. This might be propensity to buy. This might be calculating if a customer churns. This could be the right channel for activation. This could be lifetime value, etc. So this unlocks a whole fleet of downstream activities, either in the analytics space or in the prediction space. And it's not just recommendations that will benefit from that. Data aside, there's a few other steps you can take. One is better loss functions. Right now we looked at this regression loss. It's a pointwise loss, just linking a user ID, a profile ID to an error. There's a few more things you can do. First of all, having ratings is very unlikely. Most retailers or e-commerce platforms, you don't get many ratings. Think of Netflix that used to have 5-star ratings and now they pivoted to thumbs up and thumbs down. So having that is probably not what you're going to experience. One way around this is implicit ratings. You might transform your interaction into some sort of rating score. And you can, for example, leverage then, has a user clicked on an item? Has a user put it in a basket? Has a user bought it? And use this to build a score similar to a rating. How you can do this is you build a matrix P over your users and items. That's your interaction score. And then each type of interaction you can actually weight with your ratings with a weight matrix C, which means maybe a purchase is more important to describe intent than just a click. Or it might also be important that a user puts it in a basket and removes it, and you might negatively weight something that's been refunded, etc. So there's a lot to play with to optimize the score you want to train on. Beyond that, you could just say, why do we care about this anyhow? We could just say, is the user going to be interacting with this item or not? 0 or 1. We make it a binary classification problem, and this is what this logistic matrix factorization is. You can even go beyond that and say, well, why calculate all these scores and then sort them to take the 5 best ones for recommendations? Can't we just predict a bunch of interesting products in one go as a multi-class classification problem? That's also another way to look at. And lastly, with calculating these scores, we always have to compute a lot of scores and then sort them. It might be a bit of a wasteful approach. Can we not just learn how to rank the most important items directly? And this is what brings me to improving metrics. So we looked at the loss functions. They're tightly connected to the metrics as well. Right now we looked at RMSE. Obviously, to build recommendations, we would then have to calculate a few scores and we take the best ones. But why not look at how good the recommendations are directly? This is what precision at K does, for example. So we look at how many of the products that the recommender system spits out are actually going to be bought by the user in the next month. Or out of the next 5 articles a user buys or clicks on, how many have we recommended? This is this score. What if the order of the recommendations would also play a role? You not just want to find the right ones, but you want to find the most relevant and put it at the top. Then you can go to other metrics, such as normalized discounted cumulative gain. And this is where recommender systems kind of blends into search and search metrics, because this is usually also how search indices are evaluated. So now we're not just looking to find the right products that are going to be bought or interacted with anytime soon. We're also going to look at giving the right order of things. And in principle, you could use these metrics also as loss functions. And there's some research there. I think people are very much on top of this, but we're not going to calculate just point-wise losses, but maybe we can directly build models to optimize rankings in one step. So we had the data improvements, we had metrics and losses. Lastly is, can we go even deeper? And can we leverage this idea of embeddings even more? So the embeddings are quite central. These low-rank representations of user IDs, for example, they originated more in the NLP domain, but there's heavy usage of this in recommenders and also many other applications of deep learning these days. The central concept, and I'm going to show you a few examples on more active research in the field that will heavily reuse them. First of all, there's a model that used to serve, maybe still does, Google Play Store recommendations. It's what's called wide and deep. And it's very similar to what I've showed you before with this neural collaborative filtering approach. So have a look here. We have a deep model on the right, or in the middle of this graph, which is literally this MLP I showed you before, which again incorporates these dense embeddings. And then we have a wide model on the left, which is a linear model, very simple type of common machine learning model. And we can combine this into one ensemble model again and co-train this. So very similar to what I showed you before. The difference is we swapped this matrix factorization to a wide model. And the reasoning behind this is we can easily deal with numerical columns or very wide feature crosses. So we can cross many, many features, which will generate a very wide feature space, but we know wide models deal, or linear models deal well with that. And on the categorical side, we use things like demographics and some other features we can then push into dense embeddings. I want to show you some results on this wide and deep model, and that's actually on real customer data. A UK retailer, many billions of transactions, online and in-store. And there's a few things to show here. There's first an SVD approach, or the matrix factorization approach. There's an improved matrix factorization where we swap the loss to an implicit feedback and then actually tuned the parameters there a little bit. And then at the right column there is a wide and deep as we just described it. What you see here is now I also changed the error metrics to precision at 5. So we're going to recommend 5 products and see what has the user interacted with next. And NDCG, this similar kind of metric, but that also puts in the order of things. So here, unlike before on the table, higher is better. What we see is SVD serves as a nice baseline, but we can quickly improve if we switch to this implicit feedback, because here we never had ratings in the first place, so we approximated this for the SVD model. But we get definitely by far the best results with wide and deep. But with wide and deep comes also a choice of having more parameters to tune and deciding what should go in the wide part, what should go in the deep part, and how can we build these feature crosses. A takeaway message here is these deep models, maybe in conjunction with similar models or simpler ones, such as a wide one, work also quite well on real data. So this was a good first step or a second step towards deeper models. But why stop there? There's been a lot going on in the past 10 years, and I want to show you a few things on the latest advances. That's neural networks for YouTube recommendations. It's actually been replaced by a newer system I'm going to show you in a bit. But what we see down here is, again, we embed things, right? Central part is we look at search tokens, we look at video history, etc. We create embeddings, and then same story again. We concatenate this into the input layer. And we can add things like the age, we can add things like gender. Anything we know about the user goes in there. And it builds kind of the first layer, and then on top we just have a feed-forward neural network. At the top it gets interesting, because what YouTube does here is they use a two-phase approach. So they use this to train on a similar loss, but then they can also use the embeddings to do a very quick search between similar users or similar videos most of all. Why is this two-phase approach, where we have a candidate generation part and we have a ranking part? Why is this so useful? Well, think of YouTube having hundreds of millions of videos. You don't want to go and then for each user that logs on, calculate 100 of millions of scores and then sort them and take the top 20 to present back on the YouTube sidebar. You want to make this a bit more efficient, and one way is to stage this into two models. So the first one I just showed you was the candidate generation model. It uses some video context, it uses some search history and user patterns, and then via these embeddings you can actually quickly search between similarities, and you cut down the number of candidates from millions to what they claim hundreds. And then you have a second model that might be similar. Again, it uses same sort of history on videos and users. Maybe there's some other things that come into play. Maybe there's some context of what time of the day it is and what else have you been doing on your Google search, who knows. But for this final ranking, we take in hundreds of videos and then just put out the most 10 or 20 most relevant ones. So this idea is really, if you need to do large-scale recommendations, it would be very wasteful, for example, for Amazon to calculate trillions or hundreds of trillions of scores and then find their way to the best ones. You want to shortcut this, and one way is multi-stage models. Another would be optimize ranking directly and build this into the model implicitly. One last thing I want to show you is a more recent switch on how YouTube recommendation work. And there's two important findings here. First is there's a switch to sequence models, because what we looked at before is completely static. We might embed or add features on what time of the day and some temporal context, but here this is implicitly built in because the model itself is a recurrent neural network and it acts on sequences of what's been happening. So your YouTube recommendations will be heavily based on what you've watched previously. And that's an important aspect, because depending on what you build recommender systems for, this temporal context matters. For YouTube, if you watch a song, you might very like it and you want to loop it and listen to it 3 times again. But if you buy a bathtub online, you probably don't need another bathtub next week. So having this historic and temporal context might be crucial, and there's been a lot of research in the past 2 years to tackle this. So here we have this latent cross, as I said, sequence model. But this paper also questions slightly what I've been showing you in the past few slides. I'm actually going to go back, where we just throw things like geographic embeddings, gender, etc. into this first layer, and we concatenate everything. This actually works, and I hope I could prove to you that this does. But this paper also shows, while it works, it's not very efficient, because we just build one flat layer and then hope the neural network finds all the connections. There's actually a smarter way to bring together this context and the actual embeddings of user IDs, for example. And this might be happening through this latent cross, where we embed things first and separately, and then multiply it back onto the embedding vectors of user ID and profile ID, for example. And doing this embedding not at the same layer, but doing it at the 2 different steps and multiplying it at a later stage seems to yield a lot better results. And in this paper they show that the first approach, although it works, can be quite efficient, and this might be one way to account for that. But what I hopefully showed you in the past few slides is there's a lot of active research. Everything came out in the last 1 or 2 years, and the field's still answering all these questions on what are good approaches to bring in more metadata, to bring in these embeddings, and to also think about the reason of time and historical context. So there's a few takeaways here. And what I'd like you to remember is that TensorFlow can do a lot more than just computer vision. There's more to it to just building deep neural networks for image recognition, because it's a computational framework that can express very freely loss functions and optimization problems, such as matrix factorization. The high-level APIs make it easier than before to actually attempt and build such models. It's easier to build the model itself. It also has keras now fully included, but most of all makes it easier to train and to scale out if needed. To add on, it can be extended quite easily. You start with a part of the code, but if you want to change the loss function, go for it. If you want to change your metrics, quite easily done. While if you would use an off-the-shelf Python library to do matrix factorization, it's probably a bit more a struggle to do these things. What I hopefully could also convince you is that this does work. We don't just add deep for the sake of it or because we can. Adding deep components and multi-layer perceptrons, and even combining them with well-established methods, seems to yield very good results. And it's certainly what we've been doing in practice with some of our clients. And so our embeddings, they became quite a central concept in the recommender space, but even in the wider field of deep learning. And there's a lot that can be gained from calculating accurate embeddings. And there's even concepts that you would use a recommender system to maybe train embeddings on how similar users' items are, and then use this basically as segmentation. Use this in different contexts, use this in different applications of your downstream analytics or machine learning. The research here is obviously still steaming ahead fully. There's big contributions by Netflix, Facebook, Google, etc. And hopefully in a year or so, I can give a similar talk, but with completely new and even better findings as well. All right, thank you very much.